to everyone. So I will roughly, so my name is Hahn, as Frank already introduced them. I will roughly...
Lauter.
Lauter.
Das ist schon ein Lauter, was macht.
Yeah. I will roughly go through actually how to use what Frank introduced, using IBM Q experience as an example, which is IBM's quantum computing offering, which they provide through their IBM cloud, which we'll see. So at first, we go through this IBM Q experience, where we have a kind of web front end, where everyone can register and log in, and also use directly cloud accessed real quantum computing hardware devices produced by IBM. No. Yeah, it's the beta version. They released it a couple of weeks ago, so it's not super optimized in all ways. And first, before I forget it, so here we see what Frank mentioned, different real backends we can use. So there are different sizes. So first we have a simulator we can use. So actually we can directly execute the circuits without needing real quantum hardware. This is important because for the free access you get just some credits, they call it. So there's a limited amount of shots you can do for free. And I don't know if you can then buy more credits. And there are definitely also real devices. So these are earlier devices with 5 qubits. And this is what Frank mentioned. So here we can see how the qubits are connected, what is the single qubit error rates for different qubits, because they have different qualities. And what is the C0 error rate. And here we also see, which I will later show again in this composer, then we have this basic set of physical implemented gates, which are here some unitary gates with different combinations of rotations, let's say in this XYZ vectors. We have a C0 and an identity, which actually does nothing, just waits for some time, or takes some processing, which is, for example, interesting if you want to check for error rates or decoherence, because you can implement some weights, so to speak. And so they already have a 50 qubit, I think, real quantum computer. What we can access here is the second previous version, I think. It's 16 qubits, Melbourne. I think the next one is called Tokyo. And the newest one, I don't know. So what we have here is, we have this dashboard, so we can see previous results. We can use the circuit composer Frank already mentioned. And what is kind of new, what I won't use now, is we can also execute Qiskit, which is IBM's kind of SDK to use their technology and programming languages, which builds on top of Python, so it's a Python library. We can already directly execute it here through this web frontend. So we now, with this new version, it's actually not required to install anything locally, but I will use a local setup for now. So first, let's go to this composer. I already prepared 2 circuits, but we can also create a new one. And here we see we have links to some help, so how this all works, what the gates mean. We can apply some settings, and we can also see this, which is called a quantum assembler modeling language, QASM. Here you can also see how let's say, the assembler code of this graphical circuit looks like, because this is what IBM then takes for compilation and transpiling and putting on a real device, or the simulator we see. And for example, we can build this entangled states. So we can just take a Hadamard gate, put the C0, where Q0, the first qubit is the control, and the target qubit is the first one. And then we can just measure, for example, both qubits. And what's also interesting is here we also get some estimation in different ways. So whatever we draw on this or what we put on the circuit directly influences here. Yeah, it's kind of the proposed outcome of the experiment. So we can have a look at the state vector, which is just a kind of the result state we might reach. We could also, it's here. We could also look at the density matrix, for example, which shows us all the kind of the complete value space, possible space of qubit states, or also measurement probabilities. So kind of the real parts. Okay, there's something missing. Kind of the real parts of the qubits, of these alpha and beta values. So let's remove this again. So in here we will see what we expect actually. So we bring qubit 0 in superposition state and then put a controlled knot on it. So whenever we measure the first qubit as 0, we also measure the second one as 0. Or with the same probability, 1, 1. And then we can also run it. We can also run it. And here we can use real devices, like we've seen, the 4-qubit device, the 2-qubit, and the 60-qubit, and also the simulator. And we can specify different numbers of n for how often incrementally the experiment should be executed. So the number of shots they call it. Let's just go for 124. And now it will be calculated directly in the IBM cloud. And for the simulator, it should be quite fast. We should see results. Yeah, here it is. So, and here we get some metrics, like when we started, how long it took. Here, that's also interesting. If we go for a real hardware device, which I will also show in a second. Here we also see the compile and transpile circuit, because the simulator can do all gates. It's unchanged. So it's the same as the one we modeled. And here we also get the results with certain probability estimated by emulating a real quantum device with a circuit. So then I already prepared this, but we can also, because I think I'm running out of credits, so I won't go for, but I execute the same circuit. And here it's quite interesting because we also create this entangled belt state, measure it, and what happens if we go for this 4-qubit real physical quantum backend, we see here that actually, so this is a unitary, which is implementing the Hahn gate, because it does a pi rotation in around the x-axis and no phase flip. And here we see that actually the operators are swapped because of, most probably because of the backend. So because this actually translates to Hadamard C0, and we can rearrange it so it will result in this one, because these two are cutting themselves out. So that's quite interesting. Then we also get a view on the real circuit, how it got executed on the real device. Yeah. So that's it for this composer now. Yeah, and there's for sure there's documentation for the composer and for all the different gates and operators, which is under this qiskit.org domain. So here it's also described in more detail how this unitary works. For example, here we see it. So we have this theta, phi, and lambda, and basically it's p half rotation around the different axes. And here we can see that they're actually a superset of each other. So we can implement this secondary unitary operator between the third one, and then if we go here we see, for example, that the identity is just doing no rotations at all, or I think the Pauli gates, because there is a split flip around the x-axis, so we see that we just do pi 0 pi, and then we end up exactly in this south pole of the block sphere. Yeah, and the same for the other ones. So the second part is this Qiskit thing, and as I said, IBM relies on Python, and what is a really interesting feature, which is now also accessible through this web frontend, is that we can use so-called Jupyter notebooks, and therefore I want to shortly introduce what is a Jupyter notebook, how it works, for those who are not familiar with it. So actually, the thing how I present is already a Jupyter notebook. So it's a nice way of presenting code and hypertext in a really nicely combined manner. So we can write Markdown, add figures, for example, and also interactive code snippets. We can then directly execute within this Jupyter notebook, and how it works is that we have a user with a browser. Somewhere we have a Jupyter notebook server which hosts different kernels. For example, having different visual environments in Python with different libraries. In our case, we installed Qiskit, the Qiskit framework, and the different kernels, as I said. So it also works with other programming languages like R and so on. And then we have just a bunch of files, which are these interactive Python notebooks, which we can then just load within this Jupyter notebook server, and they get rendered and give us the execution environment for our code snippets. And yeah, as I said, we can have code cells, markdown cells, and we can we also have auto-completion, for example. And for example, we can just write some Python code, use any library that's available, and with also some complex formatting output. And if we execute it with Shift-Enter, we get some, for example, here's some nice HTML formatted table of our result data. Yeah, and the same for Markdown. For example, we can also nicely use LaTeX commands for example, for qubits, for quantum algorithms, for qubits, for state transformations, whatever. And they also get nicely rendered, as we can see here. Any questions so far? So you can just interrupt me, because I think it makes more sense to ask directly than waiting till the end. Okay. So then I will introduce shortly Qiskit, which is the main thing here. Just make it larger. Okay, it's a little bit dark. So actually Qiskit is a bunch of tools now. It's a complete platform SDK. And it comes with Terra, which is the core component, which actually connects the library with the real hardware, the simulators. It contains all the gates, qubits, how to work with them, quantum registers, quantum circuits, visualization. All these things are a part of Terra. And then we have Qiskit Air, which is a bunch of simulators which can be used to locally simulate quantum circuits without requiring real hardware in the backend. Then we have Ignis, which gives us, which is in a preliminary state, but it gives us access to error correction and gate error correction schemes and stuff like that. So these two are under research, or at the end of all of this. So there's quite a lot of evolution over the last years, and there are a lot of new versions coming out in a quite fast periods of time. And what's also interesting, what I will go into detail in a little bit more later, is that we have Qiskit Aqua, which is a set of quantum algorithms, actually already pre-built for us, so we can directly use them without having any idea about how the circuit really looks like we saw with this quantum composer before. So we don't have to model on this assembler level, we can just say, execute the Grover algorithm, here's the inputs. Execute this algorithm, here's the input. And then in the background, a complex super depth circuit will be generated and transpiled and compiled for the different hardware we want to execute. So, and then I also prepared a short kind of example, complete example, I will roughly go through. So actually it gives us the same things we already see in this composer, plus a lot more fine-grained control over our thing. So first we start by importing a bunch of things we need. So we need a quantum circuit, we need a quantum register, and we also need a classical register to store our measurement results. And then we also need an execute directive. We initialize a quantum register with 2 qubits here. And then, based on that, we create a quantum circuit which operates on this quantum register. And on the circuit, we add then a Hahn gate and specify which of the qubits of the register we want to apply the gate on. Same for the C0, and here we specify control gate first and target gate second, which is exactly the same circuit as we see in the composer. And then we can, so we can execute the whole thing, which I also. So we just run all these things, and then we see by this asterisk that it's currently executed. So now it loads the statements. So if we see the number, so here we, you should see the circuit. Now we see, so it's the same. And now we have different possibilities, way more than with this composer, because now we have actually access to this air backend part, where we can specify in a fine-grained manner what kind of simulator we want to use. For example, we use the state vector simulator, which actually creates a vector of a 2 to the power of n space of all qubits, which is super large. So this becomes a very fast memory problem. That's why it can't be used for arbitrarily large circuits and quantum registers. And then we just execute it and can see the results. So, and at the end, we get an output state. So the actual vector at the end of the calculation, which in this, which looks like this. And then we can visualize this by showing such or different possibilities. So like a city visualization, Hinton, Q-sphere, or Pauli vector. And for example, the city visualization looks like this. So here we have the real parts. And since we always measure eigenvalues, we only have real parts, no imaginary parts. And here we see that only the states 0, 0, and 1, 1 are possible states with a probability of 50%. And this is also what is called an exact execution, because there is no noise, there is no error, there is no gate fidelity or whatever. And what we can also do is we can do this measurement-based execution. Here we again create a circuit like the one before, plus we add measurements of the qubits and put them to the classical register we created before. And here again, we can also say, please give us the backend chasm simulator. Here we can also specify real backends, so we can connect to the IBM Q Cloud, specify different backends we have access to for the sake of paying these credits, and also specify that we want to execute the circuit. On this backend, we specify it with a number of shots. And here we get then, the number of results each. And we can also plot a histogram, for example, which shows us the overall probability of within all 2024 runs of the different.
It was a simulator.
That was the simulator execution. You can even use the cloud-provided chasm simulator if you like. That's also possible. And as far as I remember, it's also for free for certain circuit sizes and that. I think I can take 5 minutes. And then actually just super short to this aqua. And so the picture is not, so the picture is not completely up to date, it's really outdated. So what this gives us is for the different identified near-term target application domains, let's say Frank already mentioned. So IBM identified the ones that are also, I think, most prominent in literature. So we have chemistry for molecular simulation. We have artificial intelligence, like support vector machines or machine learning. We have optimization problems, like recommender systems. And we have also finance, for example. And the idea here is, so here where it says domain specific, there is not yet something provided by IBM, but they are working on it. And the idea is that, for example, in chemistry, there's a well-established set of chemistry frameworks like Psi4, PySCF, PyQuanti, and so on and so forth, where theoretical in chemistry, scientists specify their systems that they want to simulate, the molecules, initial energies, whatever. And the idea is that IBM allows them to take their models they already have and know how to specify it, drop it as an input to Cascade Aqua, and then Aqua translates this as the input for to generate the quantum circuit out of it by using different translators. For example, putting these problems into fermionic Hamiltonians or qubit Hamiltonians, which are then actually simulated on a quantum hardware device to get results back from the quantum systems way faster. And and the same idea is applied to the other domains. And the core of Aqua is then, as I said before, is that there's already a large basis of quantum algorithms, for example, variational quantum eigensolvers, or a Grover search, for example, or also a quantum support vector machine kernel estimation, which are then used for this translation to actually use then Terra to generate circuits out of it, and then put it on real hardware and run it. So the idea is to provide here an abstraction layer, like we know from classical software engineering, that we have these kind of core set of algorithms, and we can map our domain problem to a real quantum circuit without knowing actually quantum computing in detail. I think here so as I said, so there are way more than shown in the picture. For example, there's also Deutsche Joscha implemented, or Shor's factoring algorithm is already there. Also the famous HHL algorithm to calculate linear systems.
But all those algorithms have a small quantum part and some normal part, or?
No, I think they are completely quantum.
Yeah. Okay.
Yeah. I think this is part of this higher layers, because there you can actually go using Python, for example. It's quite easy because you can integrate it natively. That you specify things and then you switch using a quantum algorithm, or even your own quantum circuit, and then come back to continue. I think it doesn't make sense to go into details here. So there are just two details provided from IBM for artificial intelligence and chemistry. Maybe one thing which came back to my mind, it's already possible to move back from the classical world to the quantum world in the composer, because there's a real if. So what it allows us is actually, based on the result in a classical register, we can execute quantum gates, which is also quite interesting. So here's this if operator, and here we can say, So we can attach it to the Hadamard, for example. And then we can say, if the result is 0, apply the Hadamard, which is kind of the way back to combine classical. And I mean, it's just a simple thing. It's quite interesting. Yeah, that's it.
Good.